This is a Stanford math tournament, number theory, problem number 4. And this is the year 2021. Here's a view of this problem. A positive integer n has 4 positive divisors such that the sum of its divisors is, I don't know this Greek alphabet, let's call it O of n equals 2112. Given the number of positive integers less than and relatively prime to n is, this is phi of n equals 1932. Find the sum of the proper divisors of n. So first let's go to this piece of information. A positive integer n has 4 divisors. So we can automatically get a form for these numbers. It can either be like a prime cubed, which has 4 divisors, namely 1p, p squared, and p cubed, or it can be of the form pq, where pq are distinct primes. These two will produce 4 positive divisors. Alright, now we know that the sum of its divisors is this, and the number of integers less than this that are relatively prime is given by this phi of n. So let's first try to find phi of n for these particular numbers. So for phi of p cubed, what we want to do is we want to count the number of numbers that are relatively prime to p cubed. And since this is a prime, this is probably easy, because all we have to do is we have to take the number, which is p cubed, and subtract off from that the numbers that are not relatively prime. A number is not relatively prime to a prime if that number is a divisor of the prime, right? So let's kind of list them for p cubed. For p cubed, we have that 2p actually, 3p, and then all the way until p squared times p are all not relatively prime to p cubed because they share a common factor. This in total has from 1 to p, this is p squared. So we have p cubed total elements and we subtract off the p squared. Great. So now we can maybe get some information regarding p cubed. We know that phi of n, which is p cubed minus p squared, will equal 1932. And we know that the sum of the divisors, which are, we already stated them, 1, p squared, and p cubed, is equal to 2112. Now let's try to solve for p. We can subtract these two equations, let's call them 1 and 2. By doing 2 minus 1, we can get 2p squared, and then these remain the same, plus p plus 1 is equal to 2112 minus 1932, which comes out to be 80. So we can use quadratic formula here, or since p is a prime, this is rather easy to guess and check. If we input phi, we get an output of 56, and if we input 7, we get output of 106. So there are no primes in between phi and 7, so we know that there's no solution here. So let's move on to the next case, which is PQ. So phi of PQ, let's try to derive a formula for this. The number that are not relatively prime are all the multiples of p, so that'd be p, 2p, all the way until q minus 1, p, qp, and then union. We do the exact same thing for q. We state the q's, and then 2q, and then go until p minus 1q, and then pq. So we know that there are 1, 2, all the way until q elements here, and we know that there are p elements here, but we have overcounted qp twice, so we have to subtract 1. So we know that there are in total pq minus, and then let's do these formulas. So we know that there are p plus q minus 1 we have to subtract from. This is equal to pq minus p minus q plus 1, and you may recognize this as p minus 1 q minus 1. Okay, so we have the number of relatively prime, so we have now p minus 1 actually, better yet, I like expanding this a little better. We have PQ minus P minus Q plus 1. This is the number of relatively prime. This is 1932. And the sum, well, we have 1 P Q and PQ. And this is equal to 2112. How can we cancel this? Adding this together, adding is very easy. We get 2PQ plus 2 is equal to the sum of this. This is what, like 4044? Yeah, 4044. 4044. And then subtracting 2, we get 4042. Dividing by 2, we get PQ is equal to 2021. So, which is the year this test was administered. So now the prime factorization of 2021 is actually 43 times 47. And then the proper divisors of a number is all the divisors except that number. So the proper divisor would be 1, 43, and 47. Those sum to 91. And we are done.